The interplay between cultural ideas and technological advancements, particularly in the realms of electrical engineering and psychology, has profoundly influenced the evolution of computer science and our understanding of human cognition. This relationship has been characterized by a continuous exchange of insights and methodologies that have propelled forward the ambition to replicate human thought processes within machines. Electrical engineering, with its roots in the late 19th and early 20th centuries, laid the physical groundwork for the development of computing technology. Pioneering advancements in this field, such as the invention of the vacuum tube and later the transistor, provided the essential components for constructing the first computers. These innovations not only revolutionized the way information was processed and stored, but also offered a new lens through which to view the potential for machines to mimic human cognitive functions. The miniaturization and increased efficiency of electronic components over time enabled the development of more complex and capable computational systems, mirroring the intricate neural networks of the human brain. Concurrently, the field of psychology was making significant strides in understanding human cognition and behavior. Early 20th century theories of behaviorism, spearheaded by figures like John B. Watson and B.F. Skinner, emphasized the study of observable behavior under different conditions, neglecting the inner workings of the mind. This perspective influenced early computer science by promoting a focus on input-output models of processing, akin to the stimulus-response relationships observed in behaviorism. However, as the century progressed, the cognitive revolution in psychology shifted focus towards understanding the internal processes of the mind, including memory, attention, and problem solving. This shift paralleled developments in computer science, especially in the realm of artificial intelligence, where researchers began to design algorithms and computational models that attempted to replicate or simulate these cognitive processes. Theories of human cognition informed the design of machine learning algorithms, neural networks, and natural language processing systems, aiming to create machines that could learn, reason, and communicate in ways reminiscent of human intelligence. Furthermore, the interdisciplinary field of cognitive science emerged, integrating insights from psychology, computer science, linguistics, philosophy, and neuroscience to build a comprehensive understanding of the mind. This convergence has fostered a deeper exploration into how computers can not only simulate but also augment human cognitive processes, leading to innovations in areas such as human-computer interaction, educational technology, and cognitive rehabilitation. The symbiotic relationship between electrical engineering, psychology, and computer science illustrates a broader cultural and scientific endeavor to understand and replicate the essence of human intelligence. Advances in these fields have not only contributed to the technological marvels of computing, but have also enriched our understanding of the human mind, highlighting the complex interplay between our biological capacities and our technological aspirations. This ongoing dialogue between science and technology continues to shape the future of artificial intelligence, offering new possibilities for both understanding and enhancing human cognition. The cognitive revolution in the latter half of the 20th century marked a central shift towards recognizing the importance of mental processes and the representation of knowledge. This area saw the birth of cognitive science as an interdisciplinary field, weaving together insights from psychology, anthropology, neuroscience, and computer science into a unified framework aimed at deeply exploring the intricacies of the mind. This holistic approach significantly influenced computer scientists, especially those dedicated to the advancement of artificial intelligence, guiding them to refine their focus towards the development of sophisticated programming languages, innovative algorithms, and abstract computational models that could more accurately emulate human thought processes. As a result, a distinct separation emerged within the realm of computing between the theoretical exploration of software and the practical concerns of hardware engineering. This divergence underscored a growing priority to craft software architectures and logical frameworks capable of supporting increasingly complex and nuanced computational tasks. Such efforts reflected an intensified commitment to deciphering and simulating the nuanced dynamics of human cognition within digital environments. By integrating the conceptual models of cognitive science with the technical rigor of computer science, researchers aimed to bridge the gap between human intelligence and machine capability, fostering the creation of AI systems that could not only mimic but also extend the capacities of the human mind. This evolution in focus underscored the profound impact of the cognitive revolution, steering the trajectory of technological development towards a deeper engagement with the mechanisms underlying human intelligence and its potential replication in digital forms. The 1956 Dartmouth Summer Research Project on Artificial Intelligence was not just a meeting, but a monumental assembly that heralded the dawn of an ambitious new field. It was here that a diverse group of intellectuals gathered to discuss the then radical idea that every aspect of learning or intelligence could potentially be so precisely described that a machine could be made to simulate it. This workshop, driven by the pioneering spirits of its participants, aimed to delve into making machines capable of using language, forming abstractions, solving complex problems, and even improving themselves. It represented a bold leap into the unknown, setting a course for the exploration of artificial intelligence that would weave together the threads of cybernetics, automata theory, and information processing into a rich tapestry that continues to define the field today. This initial gathering at Dartmouth College not only underscored the feasibility of AI, but also established a foundational framework for interdisciplinary collaboration, echoing the workshop's ambitious vision across the decades. At the core of the Dartmouth Conference were luminaries such as Marvin Minsky, known for the Stochastic Neural Analog Reinforcement Calculator, or SNARC, a pioneering venture into neural network models that foreshadowed contemporary machine learning techniques. John McCarthy, notable for creating Lisp, introduced a high-level programming language that greatly facilitated the development of AI algorithms. Ray Solomonoff laid the groundwork for algorithmic information theory, essential for the emergence of probabilistic models in AI. Julian Bigelow's work on the IAS machine, an early electronic computer, Nathaniel Rochester's role in developing IBM's 700 series, and Donald McCrimmon McKay's insights into neuroscience and information theory significantly advanced the computational capabilities of the time. John Holland introduced genetic algorithms, showcasing evolutionary approaches to problem solving. Claude Shannon's foundational work in information theory provided the mathematical underpinnings for AI and digital communication, while Oliver Selfridge's work on pattern recognition and the pandemonium model influenced neural network architectures greatly. Alan Newell and Herbert Simon's development of programs that could simulate human problem-solving in games like chess and checkers bridged the gap between computational processes and human cognitive strategies, underlying the diverse and groundbreaking contributions that shaped the early landscape of artificial intelligence. The Dartmouth Workshop's profound impact set a collaborative model for AI research, integrating diverse expertise to tackle the field's foundational challenges. This assembly didn't just catalyze individual careers, but established a multidisciplinary approach essential to AI's evolution. The intellectual synergy among participants like Minsky, McCarthy, and Shannon, among others, laid the groundwork for computational models, programming languages, and theoretical frameworks that underpin modern AI. Their pioneering efforts at Dartmouth have inspired generations, cementing the workshop's legacy as a milestone in artificial intelligence history, fostering a spirit of collaboration and innovation that continues to drive the field forward. The 1950s and 1960s were fundamental decades for the burgeoning field of artificial intelligence, closely intertwined with the cognitive revolution. This era saw computer science emerge as a key player, propelling AI into a period of rapid development. Universities and research institutions in the UK and US eagerly established AI labs, recognizing the potential of this new field. This period was marked by diverse research endeavors, one of which aimed at enabling computers to understand and communicate in natural language. The creation of Eliza, a chatbot that could mimic the responses of a psychiatrist, exemplified the strides being made in natural language processing. Eliza's ability to engage in a seemingly human-like conversation represented a significant leap towards bridging the human-computer communication gap. Another research focus was on developing search-based algorithms designed to navigate through a maze of possibilities to solve problems or conquer games. These algorithms, however, faced scalability challenges with more complex scenarios due to the exponential growth in possible solution paths. Meanwhile, exploration into neural networks pursued a different approach, relying more on custom hardware than digital simulations, which contributed to the skepticism about their practical application. This skepticism was compounded by critiques published during the era, highlighting neural networks' limitations, which dampened enthusiasm and funding for farther research. Amidst these scientific endeavors, popular culture was rich with narratives that captured the public imagination and reflected societal ambivalence towards AI. Notably, 2001: A Space Odyssey and Do Androids Dream of Electric Sheep delved into themes of consciousness, identity, and the ethical implications of artificial intelligence, echoing the real-world complexities and challenges faced by researchers in the field. The 1970s heralded the first AI winter, a period marked by reduced enthusiasm and funding for artificial intelligence research. This downturn was precipitated by the failure of AI to meet the lofty expectations set in the previous decade, leading to significant cuts in government support, notably from DARPA, and a stark decrease in private investment. The AI field, still in its infancy in terms of developing practical applications, found itself grappling with not only financial constraints, but also with growing skepticism from within the academic and research communities. Philosophical and ethical debates, spearheaded by figures like Joseph Weizenbaum, began to emerge, challenging the very foundations and future directions of AI research. These discussions underscored concerns about the implications of AI technologies in society, questioning the moral and ethical dimensions of creating machines capable of mimicking human intelligence. Concurrently, the AI research community itself was divided, primarily between the advocates of symbolic AI, which relied on deterministic logic and rules, and the proponents of connectionism, which sought to model intelligence on probabilistic neural network-like structures. This division was further exacerbated by the influential critique of perceptrons in 1969, which effectively stifled interest and funding in connectionist approaches for the following decade. Despite these challenges, the 1970s were not devoid of progress. The development and adoption of Prolog, a programming language designed for symbolic AI, highlighted ongoing efforts to refine tools and methodologies for AI research. Additionally, this era witnessed significant advancements in microchips by Taiwan, which played a pivotal role in the evolution of computing and AI technologies. Taiwan's emergence as a leader in semiconductor manufacturing led to the production of more efficient, reliable, and cost-effective microchips. These advancements not only fueled the miniaturization and democratization of computing hardware, but also provided the necessary computational power and efficiency to support more complex AI algorithms and applications. This synergy between hardware advancements and software development laid the groundwork for the exponential growth in AI capabilities that would follow in the subsequent decades. The introduction of anti-logic and frames into the AI discourse marked a significant evolution in the field, challenging traditional logic-based methodologies. Anti-logic proposed an intriguing shift towards embracing the chaotic and contradictory aspects of information processing, suggesting that the essence of human-like intelligence may lie beyond the confines of strict logical frameworks. Frames complemented this by providing a method to structure knowledge and context, enabling AI systems to make inferences that reflect a deeper understanding of complex scenarios. Together, these concepts advocated for a more nuanced and flexible approach to AI development, aiming to create systems capable of handling the unpredictability and richness of real-world situations. This fusion of ideas pushed the boundaries of AI research, suggesting a future where artificial intelligence can more closely mirror the complexity of human thought. These developments, although emerging in a time of contention and financial austerity, set the stage for subsequent breakthroughs in AI, underscoring the resilience and adaptability of the field's research community. This period of introspection and debate laid important groundwork, ensuring that when interest and funding for AI research revived, the field would be poised to explore new directions with a richer, more nuanced understanding of its potential limitations.